So, hi everyone, my name is Paul Scheffler. I'm a PhD student here at DTH in the Digital Systems and Circuits group of Professor Luca Benini. And I want to present to you a paper today that we presented earlier this year at DATE called Indirection Stream Semantic Register Architecture for Efficient Sparse-Dense Linear Algebra, which was co-authored by Florian Zahuber, Fabian Schwicki, Thorsten Höffler, and Luca Benini. First, I'd like to talk a little bit about sparse linear algebra, since as you may know, sparse tensors are ubiquitous in computing these days. They occur in machine learning, computer science, but also scientific computing fields such as physics or economics. And they come in various formats and with various algorithms operating on them. One very common problem we would like to solve is to multiply a CSR or compressed sparse row format sparse matrix with a dense vector, and we call this CSRMV. And here on the right, we see how a matrix A would be encoded in the CSR format. So for each non-zero value, we have in a value array a value, and in an index array, the column in which this value occurs. And then the rows are delimited by pointers, which point to the first entry in those two arrays for each value. So how do we do in software a CSRMV product? We iterate over the rows. And for each row, we look up the values in that row, and we use the indices of these values to look in our dense counterpart vector, which value we need to multiply with. As you may imagine, this problem has a large control to compute ratio. It has low data reuse, since every value of A is used exactly once. And there is this memory indirection into X, which we will be concerned with. In the state of the art, SPMV in all of its formats has low functional utilization usually. For example, with a specialized CVR format proposed in the inter-Xeon finite landing architecture, a proposed SPMV has only 0.7% double precision floating point utilization. And in NVIDIA's AGX Savior with their own cuSPARSE CSRMV kernel, we observe 2.1% single precision floating point utilization. Now I'd like to shortly introduce stream semantic registers. They are a lightweight RISC-V ISA extension developed in our group, which is useful in accelerating data oblivious problems in in-order cores. And in such in-order cores on dense workloads, we achieve up to 100% functional unit utilization. How do they work? They essentially map registers to memory streams, as shown here on the right in an example, in a way that accesses become loads and stores, and the addresses for these loads and stores are provided by fixed stride address generators. And as we see on the example here on the right, this is orthogonal to hardware loops. So for example, we can use a hardware loop over this fused multiply add to have a continuous stream of fused multiply add instructions to do a dot product. So we get continuous functional utilization. And this is great for regular kernels such as general matrix multiply, fully connected layers, convolution layers, or FFTs. The question is, can we similarly accelerate sparse-dense linear algebra with SSRs? So let's look into this. Here we have the inner loop of our CSRMV kernel that we've seen before. Let's compile it for RISC-V. And we see that this indirection here in orange produces a lot of work in this inner loop. The problem is that SSR address generators are affine, so they work with fixed strides and bounds only. And the indirection, as we see here, even with SSRs, will still need the integer data path, which will couple the core and FPU data paths. And this isn't so great, neither for the architecture in which we evaluated it in, as also in out-of-order cores. The best we can do is accelerate sparse value loads, which will raise our maximum FPU utilization in an in-order core from 11 to 14% by eliminating these two instructions here. But ideally, what we would like to do is to perform this indirection inside the SSRs. This would allow us to once again stream the product arguments directly, as we've seen with our dot product example, and re-enable a continuous FMAD stream for very high functional unit utilization. So our contributions in this paper are first to propose such an indirection SSR or ISSR architecture, then to propose a programming model and sparse-dense product kernels for ISSRs, then to show that ISSRs provide significant performance and energy benefits, and finally to compare our solution to state-of-the-art CPU, GPU, and hardware accelerator approaches. First, what changes did we make to the SSR address generators? The idea was to do the index lookup inside the address generator by adding a read-only memory port while still staying completely backwards compatible. So we want to keep the regular acceleration capabilities. We want to do streaming indirection for sparse-dense linear algebra. So stream formats where we have an index array and a value array with coinciding indices. And this applies to the CSR, CSC, and even the general CSF sparse tensor format and variations of it. So here we see our data path in the address generator. In green, we see the original data path, and in purple, we see the added indirection data path. As you can see, some resources are shared. And I will walk you through how we do an indirection in this indirection data path. First, we load from this added memory port 64-bit index words, 64 bits, because the memory system in which we evaluated this extension is 64-bit wide. But since that is fairly large for indices, we serialize these indices into 16 or 32-bit indices to make sure that we efficiently use our memory bandwidth. Then we take these indices and shift them to offsets for the words we want to use, in our case, double precision floating point values, and add a dense access stride if necessary for our problem. And finally, we convert them to addresses by adding a base address. And now the address is ready for emission. And we can do this in a streaming fashion, so we can continuously emit such addresses as long as indices are available. So we added this to the address generator, and multiple SSRs together form what we call an SSR streamer, or in our case, an ISSR streamer, which provides one ISSR and one SSR to the FPU of our system. In our linear algebra, sparse-dense linear algebra case, the SSR streams the sparse values of A, and the ISSR streams the corresponding vector or dense counterparts through indirection. And this is the minimal setup for efficient sparse-dense linear algebra. Here, as we can see, on the ISSR, we combined the data and index ports because we prefer a limited maximum utilization, 67% for 32-bit indices and 80% for 16-bit indices, over a larger interconnect because we add an additional port to our cores. And this results in a fairly light area overhead for two such SSRs, with a 4.4 kilogate equivalent overhead in the address generator due to the indirection capability, and 24% in a single SSR, or 0.8% with such an ISSR plus SSR configuration in an 8-core cluster. So now, what system did we integrate this into to evaluate it? We integrated it into the RISC-V snitch cluster, which is now openly available. This cluster in its configuration we used here comes with 8 worker cores, each of which has a double precision floating point utilization, floating point unit with 2 SSRs, and a specialized FREP hardware loop, which we'll talk about shortly, and 1 data mover core, which doesn't have an FPU, but controls a 512-bit DMA for memory accesses, which copy data from the outside to an internal 256 kilobyte scratch pad, which is shared among the cores. So, as I just said, I think my presentation is stuck, sorry. This FREP loop, which was introduced with Snitch, decouples the FPU from the core. And this allows us to buffer and loop on FPU instructions that are issued. And this enables the FPU to work separately or in tandem with the integer core, enabling pseudo-dual issue operation. And this is very nice to keep utilization without much additional hardware. So now let's talk about our sparse-dense product kernels. The simplest case is obviously a dot product between a sparse and a dense vector, or SPVV as we call it, which in assembly is shown here on the right. There are 3 phases. First, a setup phase where we program the SSRs through a memory mapped register interface and set up some accumulators to work on. Then simply our FREP loop, which continuously executes the fmadd instruction and also takes care of staggering our accumulator registers so we don't have false dependencies between the same accumulation register over and over. And then finally a teardown step, which reduces these accumulator and writes back the result. And finally disables the SSR redirection. So as I said, the FREP loop in Snitch decouples the core and FPU execution, which means the core is free to set up the next job while the FPU is still working on the the FREP loop, which is very nice. It increases utilization. Then for CSRMV, we accelerated this further by unrolling the loops so that rows with few elements do not incur the overhead of multiple accumulators in an FREP loop, but we streamed the entire matrix in one SSR job, since as you may remember in CSR, the rows are concatenated. And then finally, we even did a CSR matrix multiply kernel, which reuses the CSRMV kernel, but introduces a 2 to the k stride so that we are able to, instead of multiplying a CSR matrix with a column major matrix, are able to keep everything row major, which is very useful. So we also demonstrated CSRMV on a multi-core cluster implementation. And for this, we reused our single-core CSRMV kernels. So here is the schedule of how this looks, and I will go through it step by step. The first thing we do is to copy the entire vector to an internal scratchpad before computation. And we use the DMA core, which controls the DMA to transfer any data from outside the cluster into the cluster. Then the DMA core double buffers chunks of entire rows, as we see here. And to dimension these rows, it will fetch the row pointers as needed, and then it will dimension the chunks by size and row count, and it will copy chunks to alternating scratchpad buffers. And while it is copying one chunk, the worker cores will work on another chunk by drawing from the current chunk blocks of n rows. And then they will run the previously presented SPMV kernel on these rows, and the number of rows they pick at once is chosen by the row count. So if you have few rows, the cores will pick fewer rows to keep balance, but if there are many rows, the cores will pick many rows so that they have a high utilization. So I also quickly wanted to talk about further ISSR applications which are possible, which weren't explored in this paper, but proposed. Many problems actually exhibit indirection, so ISSRs are useful beyond sparse-dense linear algebra. So, for example, we could do a streaming codebook decode, which is shown here. Here we have a codebook where we have high precision 64-bit values, which are pointed to by 16-bit indices, and this helps reduce data size and bandwidth. And this could be applied, for example, to quantized neural networks, value compressed CSRMV, or any other problem that is quantized or compressed. We can also have sparse or shaped stencil convolutions by storing the offsets in our stencil as indices. And this is shown, for example, here. Here we do a convolution on a 32 by 32-bit dense structure, and our stencil is encoded as the sparse structure, where we simply store the indices of the sparse structure in an array and read this with ISSRs. And finally, maybe with some added hardware, we can accelerate different scatter-gather-based algorithms. But this is reserved for future work. So let's talk about the results. First, we evaluated the ISSR in its single-core performance. So we compare our 16-bit and 32-bit index ISSR kernels to an optimized RISC-V baselines and a kernel using SSRs only. We assume here that all data is in the cluster memory at the beginning. So here we have our results that we found, where we increased the number of sparse non-zeros in a sparse-dense dot product that we did and tracked the FPU utilization. And here we see the 16-bit and 32-bit kernels, as well as the SSR kernel and the base kernel. The difference between these lines is that once we consider the reductions necessary to be part of the FPU utilization, and once we don't. But in any case, in our SPV kernel, we achieve up to 80 or 67% FPU utilization as we increase the workload or the sparse number of non-zeros. And we observe a slower convergence in the ISSR kernels because the peak that we aspire to is much higher. So we need more sparse non-zeros to compensate our overhead. Then for CSRMV, as expected, we approach 7.2 times and 6 times speedups over the baselines. And for this, we used real-world matrices from the suit sparse matrix collections with 2 to 3.2 thousand columns and 1.3 to 608,000 non-zeros. And as you may remember, we optimized this kernel to unroll roles. And this allows us to have decent speedups even for a low number of average non-zeros per matrix row, which is what we plotted here, which is roughly equivalent to the number of non-zeros in a vector if we try to compare performance or complexity. So here we see that our implementation is still significantly faster than the baseline for few elements per row, thanks to this. So on cluster performance, as I said previously, we also implemented a cluster variant reusing the same kernels. We use 8 cores in our snitch cluster. We use the same real-world matrices, and we distribute the rows among the cluster cores and keep the vector stationary in scratchpad memory. Despite parallelization overheads, we are still up to 5.8 times faster than the RISC-V baseline, with, for even one element per row, a 1.9 times speedup, and over a 5 times speedup as soon as we have more than 50 average non-zeros per row. And our speedup here is reduced by imbalance between rows, the overhead of sharing work among the cores, bank conflicts in the cluster memory, which is important, as well as instruction cache misses. And of course, we also count the internal vector transfer that is required to copy the vector into the cluster memory, since this cannot be hidden. Here we also see that we have a significant speed up even for these few average elements per row. We are also up to 2.7 times more energy efficient, reducing at its peak the energy per Sparse-Dense MAC from 142 picojoules to 53 picojoules. And even in the worst case, we have a 1.4 times energy reduction for the same problem. So now for some related work. As you may have already realized, ISSR as a proposition is similar to scatter-gather mechanisms in CPUs. These mechanisms are coming back in recent times in SIMD implementation, for example, in Intel's Xeon Phi Knight's Landing or in ARM's scalable vector extension. And our example from our introduction with CVR SRMV was on Knight's Landing, and as we've seen, it achieves only a 0.7% double precision floating point utilization, which is 70 times less than what we achieve in our cluster implementation. Then in GPUs, sparsity is tackled both in software and in hardware. For example, NVIDIA's own cuSPARSE kernel on a 1080 Ti for CSRMV achieves only 17% double precision floating point utilization, which is still 2.8 times less than what we achieve in our cluster. In recent times, there has also been proposed hardware extensions for GPU, for example, in NVIDIA's A100 architecture proposal, which is shown here. However, this supports only structured sparsity, meaning that 2 in every 4 consecutive values must be 0 or can be 0 for decent acceleration. Then finally, there are a lot of hardware accelerators that target sparsity, but most of those are hard to compare since these accelerators are not capable of general purpose compute, unlike the snitch cluster. And since often there's a specific goal, such as deep learning, these accelerators use various precision, and their goal is usually something else, like accuracy in deep learning. But nevertheless, in the paper, we show that some of the high-level methods employed by them, we can also implement in software, for example, regarding data movement. So now, a short conclusion on the work. We extended SSRs for indirection, yielding indirection stream semantic registers, or ISSRs. We propose efficient sparse-dense product kernels for these ISSRs. We evaluate ISSRs in the snitch cluster and show that they have a very small area footprint, only 4.4 kGe per address generator extension, or 0.8% in an 8-core cluster for a minimal configuration for sparse-dense linear algebra. In the single-core case, we see that for sparse-dense linear algebra, we are up to 7.2 times faster than a RISC-V baseline, with 80% or up to 80% FPU utilization. And in the cluster case, we are up to 5.8 times faster than the RISC-V baseline, with up to 2.7 times less energy needed. We compared ISSR to state-of-the-art approaches, and we found that we are 2.8 times our double precision floating point utilization is up to 2.8 times higher than in a 1080 Ti with the cuSPARSE CSRMV kernel, and we are more flexible than both GPU and accelerator approaches in hardware. So that was the contents of the paper as it was shown earlier this year. I also would like to go into some ongoing and future work. Currently, we are releasing the work in this paper as part of the open source snitch repository, which you can find on GitHub under PAL platform group. This also includes the integration of ISSR support in the snitch's Banshee just-in-time recompilation simulator. Then we are looking into extending ISSRs for sparse-Dense linear algebra by exploiting cooperation between multiple ISSRs. And we hope to achieve efficient and low overhead sparse-sparse addition and multiplication. Then we are looking into compiler support and inference of these features in high-level code. And finally, we want to evaluate various other irregular loads, such as sparse DNNs, graph problems, solvers, but also scale out problems with ISSRs to multiple clusters. So that would be it for this talk.